Chapter 4, Number 23. A swimmer runs horizontally off a diving board with a speed of 3.3 meters per second and hits the water a horizontal distance of 1.78 meters from the end of the board. How high above the water was the diving board? And if the swimmer runs off the board with a reduced speed, does it take more, less, or the same amount of time to reach the water? So we begin, as always, with our pictures. With, some nice soft water. And up here we say we have our diver running this way. Running, and this is very important, horizontally off the diving edge. So we can just say that there's only a V0x, and that's known to be 3.32 meters per second. And then the diver will follow some parabola and hit the ground, or hopefully the water, some distance. That distance I'm going to symbolize with R, and we know its value is 1.78 meters. All right, that's the horizontal distance, so this is R. And then we're going to talk about, what we're interested about is the vertical distance down, which I'm going to symbolize with H, and I don't know its value. That's actually what I'm looking for. We're trying to find H, at least in part A. So let's dive into this, if you'll forgive the pun. We know that the x coordinate will obey x0 plus v0 xt, and then plus a half axt squared. I put that in a different color because we know that that's actually 0 because ax is 0. Before I go any further, I should really have an origin of some sort, so I'm going to go here and I'm going to say my origin will be directly below the runner when he leaves the board and at the base of the water. Unless you have good reason, it's good to make the origin be the lowest, most leftmost point. That way, as many of your variables as possible stay positive. And besides being a nice way to go through life, staying positive means that the math is easier. All right, and then the y is going to be, at any time, is going to be the initial y plus v0yt plus 1/2 ayt squared. But again, we know stuff about this. The way we've made our choices, x0 is 0 and y0 is h. Also, we know that v0y is 0 because of the horizontally. And then finally, we know that it's in free fall once the person leaves the board. And so this is going to be an acceleration of minus g, which allows us to combine these into new equations that read x equals v0t and y equals h minus 1/2 gt squared. You'll see these equations a lot in cliff running problems because they generally reduce to this sort of form. This is at any time, so if I pick like over here, or I pick over here, no matter where I am, if I'm on that parabola, then these two equations are holding. What we really want to say, though, is that when we hit the water, so let's say that the time we hit at t equals, say, the time of flight, and at that moment, we know when we're here, we know something more. We know that x equals the distance r, and y equals 0, because we are x over, right? We're r over here, and we've now on this level, which is y, was defined as y equals 0. So at our particular moment, we have the things shown there, and we can take these and put them into our actual equation. So we end up with that r equals v0t sub f, and 0 equals h minus 1/2 g t sub f squared. This is useful because we've essentially decoupled the range information from the height information. And we can see that if we find the time, we could get the height, and we can find the time from this equation, which is what we'll do on the next screen. So we'll start with this second equation and solve it over. That h is 1/2 g tf squared. And then we'll go back up to this equation and we'll say, okay, well, this tells me that tf must be r over v0. And then I can plug that in over here. So I have that the height is 1/2 times g times r over v0 all squared. And I can say 1/2 times 9.81 meters per second squared times 1.78 meters over 3.32 meters per second, all squared. And that comes out to be 1.41 meters. Quick check on units. I have meters per second squared, and here I have, well, seconds squared when I do all the stuff inside. So I end up with meters as expected. So she ran off a diving board that was 1.41 meters high. Part B asks, if the swimmer runs off the board with a reduced speed, does it take more, less, or the same time to reach the water? And here, formally, we can see that we can find the time from something that has no reference to the velocity. In other words, we can invert this equation and get that the time of flight must be 2h over g square rooted. And there's no reference to the initial velocity in there, so it could not depend on that. So it must be the same time. And this is a general truth that the time of flight to move across some vertical distance does not depend on horizontal movement at all, but only on the vertical velocity at the start. So this was sort of a very shortcut compared to the other guy, but there you go.